Hello, everybody. Welcome back. In this lesson, we will go over the definition of the derivative, which will be a smooth transition from what we've learned about limits to the next part of our calculus journey. In Calculus 1, the most important topic that you're going to learn and most widely applicable topic that you're going to be learning is going to be the derivative or the process of differentiation. And we will talk about that particular topic more in detail in the next step. But what we're trying to do is to provide a definition for the process of the derivative or the meaning of the derivative. So what you're trying to achieve with the derivative is just nothing other than a slope of a given function. Slope of a function. How steep a given graph is at a given point. How can you recognize it as a function? So that is the purpose. But right at the beginning, I'm not going to give you any geometric notions. I'm going to start with just the regular mathematical definition to begin with. So the derivative of a function at a given point A is defined. So the derivative at a given point, in other words, this is the slope at x equals a of function, the original function f of x. So that slope is given by or indicated by this fancy notation f prime. We call it f prime. So with f prime, we define this new f prime is going to be this definition, and it is based on limits. That is a nice thing. And then whenever we need to compute the derivative as a function. Now here your input is a, that a could be any placeholder. It could be 1, 2. You can have any specific value in the place of a. And when it comes to the second line of definition, you have just ordinary x here so that you can prepare the derivative not as a value but as a function. So we will use both of these definitions accordingly, but these two definitions are not in fact two definitions. Those two are exactly the same, interpreted in two different forms. So to begin with, what I'm going to do is to show you how natural these computations are. I'm going to play with this definition first. And we have already seen these kind of examples under limits, but now let's play with some examples. Given that f of x equals this is the given function. Compute this limit. Compute these derivatives. Now, first of all, let me have a little space for, oh, that's bad. Let me do it carefully with slight more care. I will have a little space here, and then I will get a little space for that. Right. Now, let's perform each computation. First of all, f prime at 2. By definition, now when you have a right here, you're going to get x goes to a in this position, but now it's going to be just 2 because that's the value, the fixed value of a. And f of x minus f at a divided by x minus a. Now, oh, let me do this. The value of a should be, in this case, 2. So x minus 2. Now, if you're not seeing what I'm writing here, now pause the video, rewind it again, go back to the definition that I provided right at the beginning, right here, take a note of it, put it aside so that you can compare with whenever you do these computations. And then now all you need to do is to perform this limit computation. One thing that you can do right away is to see this is a meaningful computation. If you plug in x equals 2, you can see at the top it is f2 minus f2, that is going to be 0. At the bottom it's 2 minus 2, which is 0, so it's an indeterminate form. So since we get that indeterminate form, now in the next step, what we are going to do is, let me transfer the equality to the leftmost corner to buy more space. So 2x squared minus 3x plus 5, that is my f of x. I'm going to write it down, and minus, now I need f of 2. Let's compute it here, or you can compute it separately. What is f at 2? I'm going to do the computation right here. 2 times 2 squared is 4 minus 3 times 2 plus 5. The whole thing should be divided by x minus 2. Now, let's compute this. We need to have that computation. So this is going to be 8 minus 6. It's going to be 2 as a net sum, plus 5. It's going to be 7. So altogether, it's going to be just 7. And then there's a negative sign right here. So that negative 7 interacts with this plus 5, and that can simplify this expression to 2x squared minus 3x minus 2. The whole thing is divided by x minus 2. Now, let's do the simplification. Now, at this point, this is a regular limit computation. We have seen these kind of computations. All you need to do is to factorize the top and recognize the bad factor and get rid of that. So let's do it. 2. Okay, so one thing that I can propose, when you know the bad factor is hidden there, just start with that. Factorize it. And then what you're going to get in the other components would be, just by comparing the leading term, you're going to get just 2x right here. And by comparing the constant term, you're going to get this at the end. And if you did this properly, now let's see whether you're going to get this middle term perfectly. Negative 4x plus x, that is negative, that is going to get to negative 3x. So that's perfect. Now, after the cancellation of the bad factor, all you're going to do is to plug x equals 2 right here in the position of x, and your answer is going to be 5. So this is going to be just a computation that you're already familiar with. And let me show you one aspect. Now, if you know, when you know how to perform this computation with any number, it is not far away from computing with any arbitrary value of a, right? To do that, let me use the definition. X goes to a, f of x minus f at a divided by x minus a. And this is going to be a little bit of a computation compared to the previous one, because we're working with a parameter a. You may feel we are having like too many variables in this, but you will see, you will be surprised how simple this computation is going to be at the end. So stay with me and I will show you how to simplify this. So f of x is none other than, let me go ahead and just recall it, 2x squared minus 3x plus 5, plus 5, right? Yes. 2x squared minus 3x plus 5 minus, now if I plug in x equals a in the position of x, this is what I am going to get. It is just the same expression, but now I have a instead. Divided by x minus a. Limit as x goes to a. Now, look at the first two components. 2x squared. Now, this term and this term, after the simplification. First, you're gonna distribute this negative sign among all of these, and then you're gonna gather the like terms. What are the like terms here? 2x square is pretty much like to 2a square. Minus 3x is pretty much like to minus here, together with that minus sign, it will be plus eventually, but these two are similar. And these two values, right? Those two are pretty similar. So we are going to just gather them accordingly. 2x square minus 2a square, and then minus 3x right here, and then minus sign here together with this minus sign, that would be plus 3a, and then you have plus 5, and then with the minus sign you're gonna get minus 5 right there. So it will cancel completely. The whole thing is divided by x minus a. Now let's do the computation. Factor the common factors here. 2 is taken out. Then you have x square minus a square. And the common factors here would be minus 3. I will take minus 3 because in that way I can give the priority to a. Then it becomes x minus a. The whole thing is divided by x minus a. Now, at this point, don't be premature to cancel these kind of terms. No, you cannot do that because there's a negative sign in front, and this x minus a is not belonging to everybody in the numerator. So you need to do further factorization. This can be factored. It is the difference of two squares. So x minus a, x plus a, and then minus x minus a right here. Now, these two are going to be common factors. This one and that. Let's factor it out. And when you factor it out, you're going to get 2 times x plus a minus 3. The whole thing is divided by x minus a. At this point, you can cancel x minus a. And then the only remaining term is right here, and then x, when x goes to a, now you can plug in the value of a, and what you're going to get is 4 times, or like let's do this, 2 times a plus a, that's going to be 2a minus 3. So that will be 4a minus 3. Now, when you compute this derivative with the variable value of a, this is what you're going to get. Now, is this valid? Look at this. F prime at a is going to be 4a minus 3. That is what our observation was at the end. Now, if you look at the situation where x, or the value of a, is 2, when a equals 2, what's the value that you're going to get here when a equals 2? It's 8 minus 3, that's going to be 5. Does that validate the answer that we earned earlier? F prime at 2 when a equals 2, in other words, that's exactly 5. So you can do these computations in general form, or you can do it specifically, but it's that simple. Now let me show you the third aspect of this example. So the next one, in this scenario, what I'm going to do is to compute the derivative as a function of x. Now I'm going to employ the second version of the limit definition. If you do not recall it again, pause this video, go back to the beginning where we have the definition, right? So definition is, in that occasion, it's slightly different, but you will be surprised to see how similar and how equal, how equivalent these two are with each other. Now, what you're trying to do is, don't forget the original definition of the function 2x squared minus 3x plus 5 that will be used frequently in each computation. In the computations, why don't you use a different color? This equals limit h goes to 0. Now f of x plus h. This simply means wherever you have the variable, I'm going to replace the variable by x plus h instead of having just x. So let me do it like this. 2 times in the position of x, now I'm going to put x plus h minus 3 times x plus h and then plus 5 and then minus f of x is a plain ordinary original definition. The whole thing is divided by h. Now do the computation. Now at this point, I recommend you to uh, take a pause and then have this problem worked out yourself. Because it's going to be it's not about factorization, it's about foiling each and every step. Look at this. This is about foiling. And this is about distribution of -3. And then after that, you're going to just open parentheses and you're going to simplify. So this simplification is much more natural compared to even factorization. And what you're going to get is just cancellation. So why don't you take a moment, take a pause of this video and go ahead and do the computation yourself. All right, I hope you gave it a try. And with that, you can see x squared plus 2xh. Don't forget it is not just x squared plus h squared. There's a middle term and then minus 3x minus 3h plus 5 minus 2x squared plus 3x minus 5. This seems pretty lengthy, but you will be surprised in the next step how many terms would cancel with each other. Look at this. Plus 5 goes with minus 5. And then minus 3x would cancel with plus 3x. And then here you have 2x squared. So that term will be cancelled with minus 2x squared term. The leftover is going to be limit as h goes to 0. 2 is distributed right here with the second one. So 4xh plus 2h square and then minus 3h right here and the rest is gone. Now can everybody see? Can you see? H is a common factor to all of these. So you can factor out one of the factors and then it's going to be 4x plus 2h and then minus 3 divided by h. Cancel it. And then don't forget our limit. This limit is a unique limit. Our limiting variable is not x anymore. I put it right here. I should have emphasized it. It is just when h goes to 0. H is to indicate a gap between the 2 points that we consider. So once you plug h equals 0 in this expression, x remains intact. So 4x. This term turns out to be 0 and then minus 3. And that's our answer. Grab this answer and go ahead and check how similar it was with what we got in the previous answer. Look at that. The same, I told you these two definitions are giving you the same thing. The only thing is this is going to be helpful when we compute the derivative directly as a function of x. So the purpose of this entire conversation now is to have these two definitions employed in different computations, and without making it more sophisticated or without trying to give you the graphical or the geometric meaning behind the derivative. At this point, I'm trying to make it just computational so that you can get familiar with the computations. So as the next example, I'm going to give you a different function. And here the plan is not for me to work with this example. I will leave this particular example for you to have some practice on. And then uh, try it. And if you have any questions, if you generate any questions on that, I recommend you to uh, raise those questions. And in fact, why don't we do this? Let me give you just one of the parts. I will leave this one as a homework or as an assignment for you, and I will work with one of the pieces so that in that way we do have a starting point, right? So g prime at 1. So this is going to be just like x goes to 1, gx minus g1 divided by x minus 1, and you will be surprised to see how similar this to some of the limiting problems that we already worked with. This is the function itself, and g at 1, when you compute g at 1, it's nothing other than just 3 over 3, right? Just plug x equals 1 here. You're going to get 3 over 3. That's going to be 1. So I will just put 1 in there. X minus 1. And then limit as x goes to 1. Now do the simplification common denominator. With the common denominator, you're going to get 3 minus x plus 2. The whole thing is divided by x plus 2 times, we're dividing again by the denominator. That's going to be x minus 1. Now, at this point, limit x goes to 1. And let's simplify this. This is none other than, after the simplification, you're going to get 1 minus x. Here you have x minus 1. So that is one step away from x minus 1 when you factor a negative sign. So x plus 2, x minus 1, and cancel, cancel. And then when you plug x equals 1, what do you get? You're going to have exactly negative 1 over 3. So that is exactly the computation. Now, as a starting point for the next part of it, I will just write it down when it comes to g prime. Now you're going to do, when h goes to 0, our new variable h, the gap between the variables. So 3 divided by, here x should be x plus h plus 2 minus 3 divided by x plus 2. The whole thing is sitting at the top of h. Now, I recommend you to do the simplification of this and see how this simplification would work for yourself. Try to understand the nature. And when it comes to assignments, you will see the computations are not going to be too complicated. It's going to be most probably just a polynomial. It is just about understanding the basic level of computation related to this. All right, so with that, I'm going to conclude this lesson, which introduced us to the derivative as a formal definition, but don't forget, it is just an outcome of the limit, notion of the limit that we are already familiar with. All right, so with that, we will meet on the next lesson.